Let's discuss another application of derivative. This is maxima and minima. Alright, maxima and minima. See, when we talk about maxima and minima, now you need to understand that it has a lot of application in coordinate geometry. Alright. Now, when we talk about this maxima or minima, maxima has two different meanings in this perspective. One is local maxima, one more is the maximum value. Likewise, minima also, we have local minima and minimum value. Now, what this maxima and minima tells us is they are the turning points in a graph. Okay, let's take an example and let's try to do it. Say we are going to consider a parabola, very simple parabola. See here, you have the y and x axis. Let's say the parabola goes something like this. Fine. Now, there is one particular point in a parabola which is the lowest point. We know we call it as vertex of a parabola, isn't it? Now, that particular point is very important because before the point and after the point, the curve is going to change the direction altogether, isn't it? Like in this case, when you consider the vertex, see the vertex is V, right? So you come to this point. If you draw a tangent at this point, let's call this point as A. Alright. Say at A, you're going to draw a tangent. So the tangent is going to be something like this. Assume. So this particular tangent, like you all know, the derivative. So here f dash of x is less than 0 because the slope of the tangent is negative, right? Now at the vertex V, what we call as the the lowest point or the least value or minima. At this minima, you're going to figure out the slope. Whatever you can get, that's really not our concern. What is important for us is right after that minima or right after that minimum value. Now, if you take a point and draw a tangent, in the sense here, let's say we are going to consider this point B. At B, if you write a tangent, it's going to be something like this. Here, the slope or f dash of x is greater than 0, right? So we can understand that whether the curve is decreasing, whether the curve is increasing with respect to those points, correct? It's like those points serve as reference points. Like below this or behind this, it's like this. After this, it's like this. So they are technically the turning points in a graph. Okay. Now, practically, there are lots of applications and all these things with respect to these maxima and minima. Okay, there are lots of applications to be honest, right? Now, one example I can give you in terms of physics, that is whenever we talk about the alternating current, which is a sine curve, we need to understand the maxima and minima for those particular type of graphs. Or even in magnetism also, okay, in magnetism also, how the magnetic field is going to change, the the point where it's going to turn, all these things, it's very, very important. Like if you have North Pole and South Pole, there's a change, correct? So that change we can represent and we can figure out where is the maximum value with the help of these things. Okay, like few examples I'm giving. That's all. Now what we have is, see, you're going to have this A and B, two different points, and that vertex or what we call as the minima is where we are going to understand, okay, behind or below this one, it's going to be a reducing graph. After that, it's going to be an increasing graph, correct? So these points are what we call as maxima and minima. All right. So these are also called as the turning points of a graph. Now, this is the minima. I can do the same thing with maxima also. So for maxima, again, you're going to take a graph like this. Again, we'll take a parabola because it's easy to understand. Now, this is the vertex, the highest point. Anything behind that one or below that one, if you take it, you're going to have a tangent like this. So imagine this is a tangent. Here, slope is greater than 0. or anywhere here you take, see like this, here m is less than 0, isn't it? Now, this is the concept of maxima and minima. Now, mathematically, how we are going to do it, what we are going to do it, let's look at this one right now. Now, we are going to discuss what we are going to do in finding out this point, the turning point, what we call it, that one. That too with the help of derivative. Fine. Now, let's assume that you have a graph. All right. Let's say you have a graph like this, and say the graph is going to go something like this, some random graph. Now, there are certain maximum points, there are certain minimum points, correct? Now, there is something called as local maxima and local minima. Now, here, if you take an interval, that means let's say we are going to take from here to here. This is A, this is B. So, in the interval, interval is A comma B. So, interval is A comma B. You have the interval A comma B. Now, in this interval, see this point, this is the maximum. Let's call this as capital A. Capital A is the local maxima. All right. And let's say this is B. Point B is the local minima. That too, minima and maxima in a particular interval, not for the entire graph. Fair enough. But if you look at the entire graph, we can always tell there are other points also, right? Like see here, this point, let's call it as C. C is below B, right? Or maybe you can call this as D. D is a little above A. So what we have is there is local maxima, local minima. That too, this local maxima and local minima is defined for a given interval a comma b, like what we are writing it here. This is the given interval a comma b. Okay, now what we are going to do, we are going to understand how we are going to find which is the maxima, which is the minima. Okay, now when we are doing this, you need to understand that we have some points called as the points of inflection. All right, now the points of inflection are those where the slope is 0. In the sense, if you look at point A, see, if you draw tangent, it's parallel to x-axis. That means the slope is 0. Same thing with B also, see here, or same thing with C, or same thing with D. These are basically points of inflection, or the points where the curve is going to change the direction, right? So this points of inflection, so this one, this is the point of inflection. All of them, A, B, C, D, they're all points of inflection. So it is that point where the graph is going to change the direction, correct? Now what we'll do, we'll calculate the slope. That means first we'll take f dash of x. Suppose if this is equal to 0, then we are at the point of inflection, the maximum or the minimum, right? Now suppose if f dash of x is greater than 0, only f dash of x, then we can say that we are in the increasing part, or we can say that it's an increasing part, increasing function. This is the point of inflection. It's the point of inflection. Suppose if f dash of x is less than 0, then it's a decreasing graph, or you can say it's a decreasing curve, which makes more sense. Understood? So this is what the first derivative part, first derivative test, you can call it. Now, I'll show an example how we are going to calculate the maxima and minima, or maximum value and minimum value. Because once you understand that, application is going to be much more easier. So let me show you one example as to how we are going to do this one. All right. See the example. Say f of x is equal to, let's take it as x cube minus 3 into x square plus 5. Some value we are taking, that's all. First, what you do, you differentiate this function. All right, so when you differentiate, see f dash of x becomes 3x square minus 6x, right? Now, we first equate it to 0 to check whether is whatever the value of x we are going to get. That points are the points of inflection. So what we are going to check is, we will substitute that value in the function and check it. In the sense, first equate it to 0. You will get it as 3x into x minus 2 is 0. Or we have 2 points now. One is x is equal to 0 or x is equal to 2, correct? Now we have 2 points of inflection. Now since we have 2 points of inflection, now what we are going to do, we need to figure out, okay, so anything less than 0, greater than 0, what is the value? In the sense, take a value f of 0.5, which is very close to 0, right? So when you're taking f of 0.5, substitute this value in this function, okay, in this function. So if you substitute this, you'll get 1.5 whole cube, which is nothing but half cube 1 by 8 minus 3 into 1 by 4 plus 5. Okay, substitute. So 1 by 8 minus 3 by 4. You are going to take LCM and you're going to do it. 8. So 1 minus 6 plus 40. So now you have 34 plus 1, 35, 35 by 8. So 35 by 8 is going to be 4 point something, correct? Because 8 times 4 is 32. 8, 4 point something you will have. Whatever it is, that's okay. We're not going to look at the entire value anyway. Now, if you take f of 0, f of 0 is 5, correct? Now, I'll tell you, if you take f of minus half, the value is going to be a little lesser than 5. So, we'll check that. See, we'll do f of minus 0.5. So, what we are doing is, see, if this is the graph at 0, what we do from this point 0, we take the values within the vicinity of that particular point. Okay, why we take within the vicinity? Because see, we have 5, so this is 5, correct? At x equals to 0, you know it is the value of 5. When you take f of 0.5, see, when you took this part, you have 4 point something, so which is around here, 4 point something, correct? So the graph is coming down, isn't it? Now, what we are doing now is we are doing for minus 0.5. Let's check that also. So you have minus 1 by 8 minus 3 by 4 plus 5, correct? Which will be minus 1 minus 6 plus 40 divided by 8. Now this is going to become 33 divided by 8, which is 3.9, maybe keeps on going. That means the next value or the previous value is 3 point something, which is somewhere over here. The graph is going to be like this, right? So what did we do? We took a value for minus half, minus 0.5, and we took a value for plus half here, and we took a value for 0. That means that point 0 and vicinity of that particular point you need to check. Because if 0 is the local maxima, the vicinity points, the value is going to be lesser than what you have for 0, correct? That's what we are doing here. First, you differentiated, you got the value. Then, those are the points of inflection, either maximum or minimum. Then, to figure out is that the maximum or the minimum, you take the values within that vicinity of that given point. Like in this example, how we took for half and minus half. Same thing can we not do for 2 also? See here, we can do the same thing for 2. Maybe you can take 1.5 and you can take 2.5 and figure out, okay, is this the maximum value or the minimum value? Isn't it? Now, this is what we use, or this is how we use the first derivative in figuring out whether the point is maximum point or the minimum. Understood? This is with the help of first derivative. Now, there is one more way of calculating. That's the second derivative test. Now, in the next video, we'll discuss about the second derivative test. Alright? So, this is the first derivative. In the next video, we'll discuss about the second derivative test.